In this video, we will talk about testing the difference between means of independent samples, like testing the difference between proportions and all other hypothesis tests. This follows the same basic procedure of identifying the claim, the hypotheses, calculating a test statistic, finding either a critical value or a p-value, and then making a decision to reject or fail to reject the null hypothesis. However, each test has some slight differences to it, including which distribution is used, what the parameters of the distribution are, and therefore how we calculate the test statistic. In the case of two samples with means, we have to first consider whether we know sigma or not. If sigma is known, then we can use the normal distribution. However, that is incredibly rare, as we've seen. It is incredibly rare to do that. In fact, in every situation where we have done that, we've been told to assume the value of sigma. In reality, that's incredibly unlikely. So we're not even going to cover that here. However, we are going to therefore use the t-distribution. In doing so, we need a few things. First of all, because we are dealing with two samples, we have to consider whether the samples have the same variance or close enough to the same variance. Now you might say, if we don't know sigma for each population, how can we possibly know the variances? Because remember, sigma might be the standard deviation, but sigma squared then is the variance. You might say, if I don't know the standard deviation, how can I possibly know the variance? Well, there is a topic that we will cover in a later lesson called ANOVA, analysis of variance. And through that process, we can show that two populations have close enough to the same standard deviation from their samples to imply that they have close enough variance in their in the populations, and therefore we could use one formula to estimate the standard deviation for both samples. That being said, that's getting ahead of ourselves. We have not covered the analysis of variance, and therefore we are not prepared to do this. So these problems will tend to have two styles to them. One of them that will say that the populations are assumed to have the same variance, and one where it says the populations are assumed to have different variances. For the purposes of our class, we are going to always use the assumption that they have different variances. Now, if we use different variances, if we assume that, then we are therefore assuming that they do have different standard deviations. And that is enough to allow us to define the t-distribution as we need it. The t-distribution is, again, bell-shaped, and it will have a mean of our sampling distribution that comes from the difference between the mean of the populations, which, remember, we are assuming to be equal. That is, of course, going to be the null hypothesis. Will always include a statement of equality, which is going to put us at 0 every time. Now again, sometimes the null hypothesis is written with less than equal to or greater than equal to, but it is the equal to itself that is actually relevant. We then have a standard error, or standard deviation of our sampling distribution, which is going to come from the square root of the standard deviation of the first sample squared over the sample size of the first sample, plus the standard deviation of the second sample squared over the size of the second sample. We add those two fractions together and find the square root. This will allow us to use a formula for the test statistic, which will be equal to the difference between our sample means minus the difference between our assumed population means, which we know is going to end up being 0, over the standard error. And this is how we will calculate our test statistic. Now again, this is under the idea that if we assume different variances, that this is the formula that we use for sigma. If we are able to show through later processes that the standard or the variances of the two populations are close enough to be almost equal, then we can come up with a value for that standard deviation through a different formula, and then we would use that instead. But we are always going to assume different variances for the sake of simplicity. So we will always have this formula for sigma sub x1 bar minus x2 bar. And therefore, our test statistic will always have the formula shown here. Now, this is obviously using a t-distribution, which means we also have to deal with the degrees of freedom. Now, there is a very complicated formula for the degrees of freedom when we're dealing with two independent samples. A very complicated formula. And worse yet, that formula tends to give us non-integer values. Now, that's not a problem to have a non-integer value for the degrees of freedom if we're using technology. Of course, we don't always have that option. Sometimes, if we're using the t-distribution table, we have to have a whole number for the degrees of freedom. So what we're going to do for degrees of freedom is we are going to make a conservative estimate for it, and the degrees of freedom we're going to use is going to be the smaller of n sub 1 minus 1 and n sub 2 minus 1. So the normal degrees of freedom is 1 less than the sample size. Here, we will take the degrees of freedom from the smaller sample. Why the smaller sample? And why this simpler method of doing it? It's because the formula is very complicated, yes. And because of that, it becomes very difficult to use. It's an excessive calculation. I'm not even going to show you the formula for it. So what we do here is we make a conservative estimate of the degrees of freedom by using the smallest appropriate value. The complicated formula will often give a value somewhere in between these two degrees of freedom, n sub 1 minus 1 and n sub 2 minus 1. Sometimes even larger than either of them. But by using a smaller degree of freedom, we produce a bell curve that has fatter tails, more area in the tails. The smaller the degrees of freedom, the more area there is in the tails. The idea is that the more area there is in the tails, the larger the p-values will be. And the larger the p-value is, the less chance there is of rejecting the null hypothesis. That matters because the basis for doing a hypothesis test is to avoid a type 1 error. We are trying to avoid the idea that we may reject a null hypothesis that is actually true. So we are going to err on the side of caution and use a conservative estimate for degrees of freedom, which will then give us a lesser chance of committing that type 1 error by giving us larger p-values. So our degrees of freedom is going to be the smaller of n minus 1 and n sub 1 minus 1, and n sub 2 minus 1. Let's look at an example. The braking distances of 8 Volkswagen GTIs and 10 Ford Focuses were tested when traveling at 60 miles per hour. The GTIs had a mean stopping distance of 134 feet with a standard deviation of 6.9 feet. The Focuses had a mean stopping distance of 143 feet with a standard deviation of 2.6 feet. Does the study show does it show a difference in the mean braking distance of the two types of cars? Now, obviously, yes, the means are different, but the question is the difference significant enough to say that they are actually different for the populations? We're going to use a significance level of 0.01, and we're going to have the very common underlying assumption that the populations are normally distributed. So let's first start by summarizing this. For the GTIs, we'll call that our first sample. We have x sub 1 bar, which came out to be 134 feet. We had the standard deviation, which was 6.9 feet. And there were 8 total. For the Ford Focuses, we had x sub 2 bar is equal to 143 feet. S sub 2 was equal to 2.6, and n sub 2 equal to 10. All this information coming straight out of the paragraph there. Now, as for our hypotheses, we are asked, does the study show a difference in the mean stopping distances? It does not say that one of them should be bigger or the other should be bigger. It simply wants to know, is there a difference? So our null hypothesis is, of course, that the two populations have the same mean, and our alternative hypothesis here is that the means simply are not the same, that they are different somehow. Not necessarily that one is bigger than the other, but just that they are different, which therefore implies a two-tail test. Now, our test statistic is going to be the difference between our two sample means minus the assumed difference between the population means, which of course, under H sub O, that difference would be 0, over the square root of the standard deviation of the first sample squared over the sample size, plus the standard deviation of the second sample squared over its sample size. And then that whole thing under the square root. Again, we have to be very careful about rounding. it's in real life, it's really only a concern if we round to too few decimal places, if we round in too many values. It really only becomes a problem if our test statistic produces a p-value very close to alpha, because that rounding may have made the difference between whether the p-value is bigger or smaller than alpha. Or if we're using critical values, same idea. It produces a situation where the critical value and the test statistic are so close together that you really need to be as accurate as you can be. So we try not to round too much. In terms of doing our homework, it matters because if our value is off, then we're going to get marked incorrect, even though we basically did the whole thing right, but we just rounded too often, and that caused our value to come out just far enough off to make a difference. So if we do this whole thing in the calculator with no rounding, we get negative 3.496, etc. Now from here, we can either do the p-value method or the critical value method. I've been leaning more towards the p-value method lately, and part of that is because of the chi-squared distribution and the limitations of the t-table and chi-squared table. So I've been leaning a bit more to towards the p-value. In the real world, the p-value method is used definitely more often. So we've been kind of leaning towards that. Now, in this case, since this is a two-tail test, our p-value is going to be 2 times the probability of having a value more extreme than our test statistic. So since our test statistic is negative, it is on the left side of the distribution. We want to find the amount of area in the left tail and multiply it by 2. On our calculators, this would be the tcdf command from negative 1e99 to negative 3.496. And now we have to decide upon our degrees of freedom. Our degrees of freedom from the first sample would be 7. Our degrees of freedom based on the second sample would be 9. So we're going to use the smaller of these two, and that for us is 7. And that gives us a p-value, or a probability, of approximately 0.0050. And this is going to come out to be 0.01. Well, actually not 0.01, because there are more decimal places than the few that we show here. Because if we only use a few decimal places, 2 times our probability would come out to be exactly the same as our level of significance, which was 0.01. So in this case, we're going to want to use more decimal places. These are all the decimal places that show up on the calculator. And this is based on not rounding our test statistic and not rounding anywhere in the calculation of it, using the exact test statistic that we were supposed to have. And this time we come out with 0.01004, etc. And that is enough to show us that this is actually bigger than alpha. Now, I suppose we could have just gotten away with using the 0.01 that we got, because the idea here is the p-value has to be bigger than or equal to. And that's how we fail to reject. So we could have gotten away with it based on the equality, but I like to show the reason why we don't round and why it matters. If we had used a different test statistic because we either rounded in the calculation of it, or we used a rounded test statistic in finding our probability, or we then rounded the probability and used that to get our p-value, in any of those cases, it's very possible that what we got at the end could have been just a little bit smaller than 0.01. If our test statistic came out just a little bit bigger, our p-value would have come out just that little bit smaller, and it would have been enough to change our decision. So in this case, it's a very, very close thing, but we will fail to reject h sub 0. So at the 0.01 level of significance, and that's really important to say here, because if we change our level of significance, it will definitely change our decision. At that level of significance, there is not enough evidence to, in this case, we did not actually specify a claim. We just asked, does the study show a difference in the mean breaking distance? And in this case, based on the decision to fail to reject, h sub 0, that means we are accepting h sub 0. We are believing that they are indeed equal. So we'd say there's not enough evidence to show a difference in the mean breaking distance. Now, that being said, we should also consider the fact that our p-value was incredibly close to our level of significance. And it's a very small level of significance compared to others that we see often, like 0.05 or 0.1. So we do have a pretty extreme test statistic. Negative 3.496 is pretty extreme. So that being said, we should recognize that our decision to fail to reject was by a hair's breadth. If we had any other level of significance of the common ones, we would have definitely failed, or we definitely would have rejected h sub o and shown a difference in the means. That's one reason why, in statistics, the choices we make matter. A slight change in the level of significance could have changed our decision entirely. And also why we don't round, because as I said before, a slight difference in the value of the test statistic, either because we rounded in the calculation of it, or we rounded the value of the test statistic itself in finding the probability, any of those things could have changed our decision because of how close our p-value ended up being to alpha. So be very cautious about rounding. You never know how it might make a difference.